Hello and welcome to another episode of the Measurement Lab. I am your host, Elijah Carey, and I'm really excited for today's topic, object-oriented programming in LabVIEW. It's something that I personally have become a big fan of, and I think once you really understand it, it's hard to program in LabVIEW without it. And so I'm really excited to be joined by one of the fathers of this technology, or the inventors of this technology in LabVIEW, Mr. Stephen Loftus-Mercer. Stephen, welcome. Thank you for joining us. Give us a little bit of background on when you first joined NI and the first version of LabVIEW that you worked on.
So I joined NI in 2000, Y2K, and I was there for 22 years. The first version that I used was version 6, and then 6i. 6i is the first one where I had even that I was using, but then 6.1 is really where I had my first features go in.
Okay, and you joined as a member of the LabVIEW R&D team at that time?
Mm-hmm.
Okay, so background, you're a computer scientist by trade. So you came in with a lot of background in other languages and computational models, right?
Yeah.
Had you used LabVIEW before joining NI?
I did not know that I had. I worked with a number of other engineers who kept handing me these models that I would then translate into C++ code in order to deploy on the robot, without knowing that if they had just told me that this was LabVIEW, I could have deployed the LabVIEW code directly. So I spent a good portion of my senior year rewriting LabVIEW code in C++, working just from running front panels and trying to match the graphs.
Oh, you said LabVIEW 6.0 was your first version of LabVIEW that you worked on. Okay, so at the time, of course, LabVIEW didn't have classes, and I don't think there was really any concept of classes. Of course, we had type defs. So help us. Do you remember the journey you went through when you kind of arrived at this concept and where it evolved from?
So I was asked during my job interview, what do you think are the most important things that LabVIEW needs in order to keep up with modern programming? And I gave a whole kind of mini dissertation on the value of object programming. But at the time, my understanding of data flow was fairly weak. And I had a whole lot of concepts of memory management and everything that just didn't belong in G. And when I joined the team, I worked on, I kind of lucked into working with the person who was taking the lead on designing objects. And he left the company, and I was kind of left holding the bag because I was the one available to take it. Well, I started working on this, and Jeff K actually saw some of my notes on a whiteboard as I was drawing them up and trying to make some things work. And he's just shaking his head. And I did not know him very well at the time. And he's like, you don't understand. And he called a lunch with all of the senior LabVIEW programmers and basically sat down and said, all right, we're going to walk you through why is this data flow and why isn't this data flow? And at some point while they were hammering me on that, I finally grasped what was really elegant about LabVIEW, why it was even calling to me in the first place. The way that, the thing that someone pointed out is, we don't handle arrays by pointers. We don't handle strings by pointers. Why would we handle anything by pointers? And when I realized that refnums were not the answer, but refnums were the crutch by which we made hardware work, because nobody had been able to fix that problem, I was like, okay, well, what do I do without the references? And all of a sudden, once you asked the question the right way, the card deck just sort of folded together, and everything came out nice in order.
I think it's interesting for context too at the time. It's not like, in this modern era, I think object-oriented programming is just such a universally adopted concept. It's fairly ubiquitous in all modern languages. But at the time, I wouldn't say that was the case. In fact, let me put that to you. Put it in the context of the prevailing sentiment regarding object-oriented programming at this time. And
it was definitely the ascendant view. I mean, Java and C++ were both the languages to know. Java was considered, the best training language most universities were basing on. You didn't want to do raw assembly anymore. Everyone knew that. C code was for when you had really strict performance requirements and really needed to be rigorous about your multi-threading. But anything at a higher level, pretty much the conversation was you need to be using an object model of some sort. Pendulum has swung back and forth in and out of that over the years. And the trickiest part is that Haskell and Lisp, the functional languages, never really went into the object paradigm at the time. And because they were all reference-based, objects were always associated with references. And there were a whole bunch of programmers out there banging pots and pans and going, you're going down the wrong road by reinforcing all these references, which can't be multi-threaded, can't do compiler optimizations, can't do all these things. And are essentially unsafe memory management that the program has to worry about. And so when I started prototyping in LabVIEW, I was actually going back to Haskell and doing prototyping there of what would an object model look like in Haskell. And they essentially have that today with all of the type inferencing and type, compositing. They never went to objects truly in the same sense, but it's all very, very similar at this point. That idea of encapsulation and packaging things together and limiting who has access really is the core of most languages these days, and just making code readable.
Well, I want to ask you more about exactly that and the utility and value, especially given that most people who are using LabVIEW are not, as you are, a computer scientist by background, and then come back to some of the design decisions and philosophy that went into the model as it currently stands. But for somebody watching this who may not have used OOP or might even be scared to adopt OOP as a convention in their programming, what would be your elevator pitch to them in terms of the utility and value it can provide, especially in test software?
Well, it's been a long time since I've encountered anyone who was afraid of adoption of it. I've met people who had difficulty adopting it, plenty, but there seems to be a prevailing wind. We've actually gotten through the community that is basically you need to have this as a tool in your toolbox. And so I haven't really met anyone who's afraid of it or thinks it's overly complicated, but just getting their head around all of it, I mean, that's a skill that comes with time. You start with the idea that, okay, I'm going to build a cluster, and that's an easy concept because it just means I'm putting a bunch of independent elements together in a block and I'm going to carry them around on a single wire. Great. Then you take the next step and you say, okay, I'm going to seal up that wire and I'm going to limit who can even see inside it so that most callers, most handlers have no idea how it's implemented. And some people were like, oh, well, that just makes me have to jump through oops in order to get to my data. And the reality is no, that makes it so that certain parts of your program aren't dependent on your insides, and you can freely adjust the insides without breaking every section of your program, and forcing a whole bunch of rework for small changes. It turns out that the more you can put up walls around your data and around your functions, so that you limit the access points, the more flexibility you have in the entire system to change a part without its changes rippling out across the whole system. And so you seal up that cluster as a class, and you say, okay, that's the private data. Now I'm going to give you some accessor functions. Here you go. And then you're like, actually, accessor functions are kind of, I've got a lot of these salting all over the place. I read one value out, I do some work, I write it back into the object. This is a really mess. What I really want is truly methods on this class that are the operations this class actually needs to do. Stop writing so many accessors. You start writing actual functions that are members of the class, and suddenly your level of functions comes way down. What I'm essentially describing is the evolution. I've taught many students in college over my career of a freshman to a senior in computer science. Is you start off, okay, I know how to shove all these things together, and then I have one tool that I use to yank them back apart. And then over time, you develop a sense for what is the best way to pack them together and better tools for, reaching inside that sealed container. And as a programmer, the more you work in it, the more intuitive it becomes.
So in terms of the I mean, all that drives with my experience, the natural evolution from a cluster and then the encapsulation of it and the methods. I think the thing that, to your earlier point, um, it has become far less intimidating for a lot of our users. And that gradual approach, the graduation from clusters and the mother cluster, and eventually recognizing the value of compartmentalization and encapsulation of that. I think that is an evolution I've also seen a lot of people go through. I will counter. I think that the sentiments around OOP very widely based on region.
Mhm.
And I think there's a lot to be said about the influence and advocacy of our users, and you can see these very large areas where it's been very widely adopted, and then conversely, there are certain uh, communities that are still very reticent for a lot of the same reasons that you may remember from 10 years ago, where they just find it as this mental leap that they're not ready to take. And I think some of the typical concerns relate to the readability of code, the number of files that they end up having to manage independently, and they perceive it as a fundamentally different paradigm shift. And so, what would you say to anyone watching that has those concerns? Like, what's the value and the reason they should be willing to take that plunge, as it were?
Yeah. I mean, I don't have hard numbers to make this claim, but anecdotally, we all talk about how much more productive a G programmer is over a C programmer, just because you've got your code, frankly, better organized, better able to see, and data flow, flows better. That same advantage frequently goes to the OO programmer over the non-OO G programmer, because your code is better organized. Your ability to say, okay, I need to fix this function. Where in this pile of code is this function probably live? Goes up, because instead of looking at an alphabetical list of every VI in your entire application, you're able to say, well, it's part of this object over here. So I go to that class, and now it's a much shorter list of possible functions that is where this is. A lot of your development concerns of, can I even make this fix without breaking code? It's a lot faster to fix because I know the scope. I can say, oh, but that's a private function. I can freely change it because I can see all 6 callers, and I know that they're all in memory, and I know that they're all available. And I can check my interfaces and verify them. I can learn a piece of code as, let me learn this object in isolation, this one class. Let me see what it does. Let me pull it out into a separate application, play with it, test it, and I understand it without having to pick up the entire scope. Whereas with a cluster, frequently, if you want to understand what all is in there and what are the levers that are available to make it do different things, it's spread out through lots of parts of the code. It's all about organization, really. At the end of the day, that is the only thing that really objects bring to the table, is a better organization of the code you would have written anyway.
And would you agree it's the same value proposition in LabVIEW as it is in any other language that's object-oriented?
I think so.
Okay. Let me ask you a more provocative question. Throughout the years, there's obviously been a divide between people that prefer the by value approach, which is, of course, the native approach that you designed, and a more by reference approach. Mm-hmm. And I know, per your comment earlier about the pointers in memory, the references, you're a staunch advocate for the by value approach. Would you concede, is there ever any use case in which a by reference approach is the better approach?
Well, the trivial one is when all the by value approaches have failed and you've already accepted it. Yes, there are use cases for references, or we wouldn't have them in the language at all. Those use cases are getting fewer and fewer as LabVIEW matures as a language, but they do exist. There are times when having a central data store and just reading that global variable is useful. And a DVR gives you a dynamic way of spreading that data out, or essentially instantiating global VIs on the fly. there are some, odd ways of representing hardware, because they are singletons in the environment. That's frequently nice. My preferred way these days to represent a piece of hardware is with a running VI, not with an object that I talk to. And the state of that hardware is represented by an object inside that VI. So I still have
is that you might refer to that as an actor, perhaps?
That is one way, but
Okay.
any sort of VI reference, or a VI reference, a Q reference, an actor and Qer, those are still references. References to data become just fewer and fewer as time has gone by. The introduction of the channel wires really struck them down out of my code.
Really? So you think that the advent of channel wires in some ways is an alternative approach for a centralized data reference?
It can certainly make the programming of that a lot easier. You can think of it in more direct terms. It doesn't necessarily, at the heart, the replacement for the data value reference is the running VI reference that is the stateful thing, and you communicate with it. And when you've got those singletons of hardware, there's still use cases for references, but they're never your first reach, or at least not if you're on one of my teams. The performance impact is just so substantial to having to lock the reference, look it up, get its value, do whatever the operation, and that, creating friction elsewhere. The lifetime management of trying to make sure that you closed what you opened, the risks of, weird state propagating in places, and just the untraceability of the reference where you can't necessarily find all the places it's doing. Even just jumping from an in queue to a D queue, even when the queue wire is routed somewhere, it's still up the wrong direction from the data flow because it's some common color coming down. So, I've certainly used them. I don't deny it, and they're valuable, but and they are your final line between you and the next piece of hardware, between your network connection, all of these things. But they're not in the core of the program. They're not in your business logic as much as possible.
So let's double click a little bit on some of the work that you did to ultimately deliver classes as a feature in the product. The first release of LabVIEW that had classes in it was
2006 8.2.
8.2. There was no vestiges of classes in 8.0.
It was in the beta. It never released.
Gotcha. So I'm curious I think for my own personal curiosity and those watching, help us understand the nature of the work you had to do to bring classes into being. Was it largely editor Chrome around clusters as they were, or was there a lot of back-end changes that were required to support them?
It was 5 years of refactoring large portions of LabVIEW. We needed an entirely new type descriptor system under the hood. That's the 2D array of N16s that you see if you use the old form of the flattened string, that has the type descriptor. That whole array, we needed new encodings there. We needed, new behavior for flatten, unflatten, the comparison primitives. Lots of new code gen abilities for different types of indirection in order to make accessing, this pointer structure efficient. The whole drawing wire colors, the custom wire editor.
The dynamic dispatch terminal.
Yeah, a whole new way of doing the call VI node. New tags on the VI itself because there's now a new configuration setting.
So it was a pretty comprehensive rewrite of a lot of the internals of LabVIEW.
It was here, and let's not forget that was on top of when we started, we didn't have a project or a library, and a class is a specialized library. A new type of control VI, the private data control that's inside the class. There was a ton. There's not many sections of LabVIEW that weren't touched. Like, I didn't have to touch the networking code. The actual assembly emitter didn't get down there, but none of the graphics layer had to change. The graphics we drew, obviously, but I didn't have to do that. But it's easier for me to list the parts of LabVIEW that didn't get some amount of touch from my team than to list all the things that we did.
Wow. Yeah. I mean, and they, it really is. I meant it earlier when I said it's so hard to imagine writing LabVIEW code without using classes, at least for me. And I know for a lot of people that use them on a regular basis. So it's a, I think, transformative tool once you really feel comfortable with it. So in terms of common patterns with LabVIEW, of course, they're the foundational design patterns around how LabVIEW code is architected. I know when you and I, one of the projects you and I discussed many years ago was trying to help people understand how to adapt design patterns from the greater CS world to LabVIEW, enabled in large part by the advent of classes in LabVIEW. What are some of the key design patterns that you would encourage most LabVIEW programmers to familiarize themselves with, especially if they're familiar with classes?
I don't have that information at my fingertips these days. There's a website on ni.com. If you go look up OO patterns that I started years ago, people have kept it up to date. I saw some edits on it earlier this year. It doesn't change very often because those are kind of like standard. But if you search around for it, you can find that link, and there's example applications and everything.
I expected you to say the factory pattern. I expected the factory pattern to be one of the go-to ones.
That's one. Like I said, I off the top of my head, I wasn't thinking about them. Factory is useful if you're building parsers. If you're trying to take a data source and somehow get it to be, I've got different modes of operation depending on what thing comes in. Then I'll produce the necessary object to match this input. Or translate a user selection into the behavior you want to plug into your system. Both of those are useful factory. Just the basic abstraction pattern of for plugins. I don't tend to use some of the more arcane ones, the decorator and stuff. They're useful in niche situations, and you should.
What do you tend to use?
I don't know. I don't tend to classify it that way.
Do you use a lot of Active Framework as your go-to pattern? And we're going to talk.
I mean, when I'm writing on my own, it's been a while since I've done much on my own programming. And at my employer, we had a whole different architecture. But I don't know. I have not really kept count of which patterns I pull out of.
That's fair. Well, let me ask you this. I mean, if we've spent a lot of time on the history of classes and the evolution from type defs to the original advent of classes, but more recently, there's been a continued evolution with the advent of interfaces, as an example. And so I gather that was something that you would have had at the initial release, but I obviously it was more work, but I think there was also a lot of thought that went into the design of interfaces. Can you provide some background on those?
So interfaces, I wanted to do them in version 1, and yet it waited almost a decade and a half before we actually got them. They were conceptually out in the world as a better way of doing certain types of inheritance, and in particular multiple inheritance, which is the concept of you bringing behaviors from different classes together and unifying them, and allowing a single object's data to be transformed by different APIs. And James Gosling was the one who introduced them to me in a lecture. He's the creator of Java, and I had the joy of actually getting to watch one of his lectures once. And got enough in that hour and a half to really shift a whole lot of things. But he had some very choice words about multiple inheritance in C++ and the other languages that had tried it. and the horrors of what it was doing to performance under the hood, the confusion that it was introducing to users of those classes because you couldn't ever tell, what was it? I've just shot myself in the foot. I don't know if it's the left foot, the right foot, or maybe it's a hand. That was one of his comments.
And yet we were getting asked for multiple inheritance all the time.
It was a constant drumbeat question. And the consensus from the programming world that I was hearing, and I stayed in contact with my professors back at the university. I knew I had some contacts to get some questions to Bjorn Strustrup, who created C++. I was feeling out the world. And the consensus was, you don't need it. Don't use it. Find a different way. But Java at the same time was saying, but we've got this whole other concept of interfaces that works cleaner. And essentially an interface is just a class with no data. It's got a bunch of methods, no data. And you're like, what use is a class without data? And you're like, well, not much, except that it defines a whole bunch of interfaces, connector panes in the parlance of LabVIEW. And it says, this is the set of operations. And if you fulfill this set of operations, then you can plug into all these algorithms over here. And they should have been simple. Like, you just get rid of the private data control, right?
Right.
Turned out that there was a lot more that needed to be done. But when we finally did it, it took about a year from start to finish to get interfaces in there. It was not the same keelhaul the world that putting classes in the first place was.
Well, for the uninitiated, I typically think of the person that defines lowercase interface or the connector pane to a method as the parent. And so help us understand the difference and why not just define said interface in the parent versus having a separate interface class.
So we have what we talk about in the LabVIEW documentation is one parent class, many parent interfaces. So an actual class that you're really going to use, that your business logic may have multiple parents. And one of these classes brings data to the table, and the others are just bringing interfaces. And what that allows is the new class that you create can then be used, upcast, cast two more generic on any of these places that it eventually ends up going. And that allows you to do, to take the state of a given object, pass it to different subsystems, reuse code that is meant for wildly different applications, but has the same general, I need you to churn in this particular manner. The classic easy example is the sort 1D array has if you create an interface that is the comparison operation, then you can inherit the less interface and put it on an object. And now every object that has a less interface can go through there. It's not actually how we did it for the VIM, but that's the classic example that a lot of people will reach for. Just put this interface on it. Now it's sortable because you defined your less than operation. And there's lots of cases out there where I want to do generic handling of data, but I don't know the specifics of how these bits change in that operation. And so you put the interface on lots of things. Printing, serialization. There's some interesting things around configuration. Use this object as a configuration for that. The big one, use this object as a support for a user display, where the display has to read the object and say, what color are you? Well, the DAC, the object that represents the DAC device and the object that represents the network both have the ability to give a status as a color. And don't actually mix your interface and implementation. They both emit a status good, which the UI will then interpret. But these are unrelated hierarchies. But what they implement is a common, status indicator interface. And so both of them are capable of being passed to the same UI element, which is then able to show create status.
So, Stephen, I'd be curious to get your take on a question that was put to me by one of our architects recently. He made the observation, or shared the observation, that he feels like when people use classes in LabVIEW, they tend to gravitate towards a lot of inheritance as like one of the primary techniques that they use. And he was asserting that due to how we teach classes, that there's an overuse of inheritance in LabVIEW. How would you respond to that?
It's possible. I will even go with probable. You can't not teach it. And it's an important tool, and it's an important tool to know early on. And I've never really come up with a good way to teach when not to do it. I mean, I had a whole lecture series on behavior, state, and identity for deciding, is this actually a valid inheritance?
Good.
And, you know, it's a part of the OO course last I looked. But that's still a very hard thing to get your head wrapped around, is to really see this is appropriate use. This is going to cause me more problems than it solves.
It's like interesting. The concept is actually not that hard.
Yeah.
Helping somebody really know when it's useful and applicable is the battle. And he was advocating for, we need to help people better understand its use purely for encapsulation. Right.
And you know, composition, not inheritance, has been a rallying cry of a lot of systems. The interfaces have helped a lot with decoupling a lot of that, because people aren't trying to shove everything in through the inheritance tree. So that's, I know, at least in a couple of systems, that's taken the weight off. I haven't had a lot of contact with the wider LabVIEW community for a couple of years now. So I've
been locked away working on some important projects. So
I only know a couple of people how the interfaces have affected them, but if it's like I've seen in other programming environments, that should have cut down on the amount of overwrought inheritance, because it was the only tool you had to get interfaces cobbled together. And so
I suspect there's still a need to create more awareness around interfaces in the LabVIEW community. But Stephen, I want to end with just a look towards the future. And I know, of course, you've since left NI and moved on to some other really exciting projects where you're using LabVIEW. But both as somebody who worked on the technology and who continues to use the technology, maybe just share like some of your hopes and your vision for the future, specific to the LabVIEW language, because I think a lot of your work, and this work specifically, has been around enhancing the value and the capability of the language. So as you think about the future of LabVIEW, what are the things you're excited for and hopeful for to see in the language in particular?
So it took my brain spent a lot of years working on LabVIEW, and it continues to innovate on it. I did just put up on the Idea Exchange like a month ago. I finally have worked out how I would implement lambdas. Call them what you will, functors, lambdas, on diagram functions. You can find it under the term quick classes, because I took a very different approach to make them appropriate for data flow. And I'm now, it took me many years of lying a whole stack of notebooks over here. But I put it up, and it's there for the LabVIEW team to take if anybody wants to run with it. But it's definitely what I would be implementing if I was still working on it. Continuing to drive Jeff K's channel wires to the point where they're clean network connections, and we can actually draw the distributed graph. I would be returning to the concept of a system diagram. It was a right idea. It wasn't ever executed on correctly, but the concept of the project tree is a failure. It should have been a graphical model showing how your pieces come together, and here's how your code deploys.
That's interesting.
A run button on the project that says this is what it means to run this system. That would, there's not a programming language in the world that I've ever seen that has actually taken all the hardware and the whole programming environment and made it a part of the language to actually say, I can express things about the deployability, the upgradability, the revocation, make that a part of the language so that you can talk about in full reflection the modules and how do you compose them together and the dynamic loads and everything. We've gotten very good at inside one computer, inside one application, but we've never taken the steps to talk about the whole thing as a multiple set.
Hence channel wires, right? I think I see your point.
Is a first shot at that, which says, hey, I can express, this is the FPGA, this is the main desktop, look what I can do between them.
Interesting.
And the FPGA channel is the only one that, as the last time I checked, is the only one that is there for cross target communication. But there's a whole raft of things we can do to expand that.
Certainly is an important trend. Just had another episode talking about, gRPC and containerization and having these independent modules able to communicate with each other.
Right. And the gRPC stuff is a great low-level thing, but it doesn't rise to the level of express the deployment of LabVIEW code to a target, express the shutdown of that code on that target, and give it to me all in a graphical representation that I can look at and say, yes, that matches my schematic, or is my schematic.
These are interesting ideas. And I want to thank you again for your passion, your advocacy. I think classes would not be what they are today were it not for your leadership and your vision. And I know I'm a huge fan. We're going to have you back to learn more about how those technologies then were parlayed into things like Actor Framework. So look for that episode. And in fact, be sure to like and subscribe so you get notification when we release that one. But Stephen, thank you so much. Thank you for joining us today and for all of your efforts to make LabVIEW the language we all know.
I hope it keeps growing in the future. It's certainly been useful to me.
Thanks, Stephen.
Have a good one.